Hello children, welcome back. We have the new chapter, chapter 9, Mechanical Properties of Solids. In this chapter, we begin with elasticity. Elasticity is the property of all material bodies due to which it regains the original dimensions after the removal of the deforming force. Then generally based on that, bodies can be classified into three: elastic bodies, then plastic bodies, third one elastomers. Elastic bodies are those bodies on the removal of the deforming forces regains original dimensions, and also large amount of deforming forces are needed for producing small deformations. But plastic bodies are those bodies which do not regain original dimensions absolutely after the removal of the deforming forces. At the same time, elastomers are those bodies which would regain the original dimensions, but it needs only very little deforming forces to produce large deformations. So generally three categories. Elastic bodies are more stronger. Solids are highly elastic. Elasticity is the measure of mechanical strength. Different types of elasticities are there, depending upon the different types of deforming forces which can produce temporary deformations in materials. Like if you make elastic deformation in the length, a solid may have, a substance may have the basic property of length, maybe a string, maybe a wire, maybe a rod. All that when you try to deform lengthwise, you try to increase length or when you try to decrease length, that body itself tries to resist that changes. So the body has got its own resistance against the changes that we make, for which there will be some sort of internal restoring forces developed inside. That internal restoring force per unit area is defined as stress. That percentage deformation occurring temporarily is called strain. Elasticity is measured as the ratio of the stress and strain. Three types of elasticities, three types of stresses, three types of strains. Linear stress, bilinear strain is Young's modulus of elasticity. Shear stress by shear strain is called shear modulus of elasticity. Volume stress by volume strain is called hydraulic modulus, bulk modulus of elasticity, volume modulus. So three types of elasticities: Young's modulus, shear modulus or tangential modulus. Third one, bulk modulus or hydraulic modulus, volumetric modulus. So three types of elasticities basically. All elasticities arises because of interatomic forces. Elastic forces are electric origin. Tension is an elastic force which is of electric origin. The basic fundamental force is electrodynamic force. Three types of stresses, three types of strains. Stress has the unit as that of pressure, force by area, Newton per meter square, Pascal. Strain doesn't have any unit. It is measured in the unit 1. Only that unit, no other units. Percentage, it is expressed in percentage. 1%, 2%, 0.5%. Basic, the comparison is with 1. So that itself is the unit. But practically it doesn't have any unit. Stress has a unit as that of pressure, Newton per meter square. Stress is not a vector. Stress is really a tensor. It is neither vector nor scalar. But strain is a scalar. Stress by strain is elasticity. Three types of elasticity. Now, how to measure this stress? Stress is measured differently in different types of elastic deformations. When you try to change the length of an object, its length changes temporarily, its area changes, radius changes, but its volume does not change, but its shape changes. If length and shape changes, that type of stress developed is called linear stress. In a string, the type of linear stress is called tensile stress. A string can only sustain tensile stress because when you try to increase the length of the string, the internal restoring force inside the string tries to restore the length. Then that internal restoring force tries to decrease the length. The deforming force tries to increase the length. Restoring force tries to decrease the length. That is called tensile stress. So tensile stress is nothing but the tension per unit area in a string. So tension per unit area is called tensile stress. Both length and shape changes. The second type is shear stress. When you try to change the shape only without changing length, without changing area, without changing volume, only purposefully we are changing, deliberately we are changing the shape, twisting of a wire, twisting of mustache. Shear means about shape. Shape only changes, that is shear. When a spring is loaded, the spring extends. The spring extends, but the wire does not extend. Okay. Here, that's why the length, area, volume, nothing changes for that wire using which that spring is coiled. That's why only shape changes. That's why the stress developed in a loaded spring is shear stress. It is a previous scheme question. The third type is hydraulic stress. If there is only volumetric changes, nothing else changes. Length, area, volume, nothing changes. Only what changes? Volume changes. Maybe that surface area temporary change. We neglect that. The change of that will be negligible. For example, a metallic sphere immersed under few kilometers of water. That metallic sphere is under tremendous hydrostatic pressure, due to which there is a small percentage decrease in its volume. There is no change in shape, only change in volume. That's called hydraulic stress. Hydraulic stress is numerically equal to the applied pressure. That's also previous question. Hydraulic stress is numerically equal to the applied pressure. So, stress and strain, different types of stresses, different types of strains. Young's modulus, bulk modulus, shear modulus, different types of elastic moduli. Now, we'll continue with each of those specifically. First one is Young's modulus. Young's modulus. The letter used is Y. Young's modulus is equal to linear stress by linear strain. So linear stress is F by A, where that F is the restoring force. And that area is the cross-sectional area, perpendicular which that restoring force is developed. Divided by linear strain, delta L by L, so formula becomes FL by A delta L. Young's modulus is basically property of the nature of the material. Young's modulus would not change if you load it or unload. Young's modulus would not change if you increase or decrease its length, radius, but Young's modulus changes if material changes. Steel has highest Young's modulus. You can refer to the tables in your textbook. Steel has highest Young's modulus. Young's modulus finds its highest value for steels. And the graphs all I will explain. So you can see Young's modulus of steel is 200 into 10 power 9. Young's modulus of iron is only 190, slightly less. Young's modulus of aluminium is much less, 70. Copper 110. Young's modulus of steel and copper nearly ratio 1:2. Young's modulus of steel is nearly twice the Young's modulus of copper. Young's modulus of concrete is much less, 30. See, we use concrete buildings. If you move on to steel buildings, steel beams, it will be so safe. Developed countries use steel beams for buildings. Bone has only 9.4. Polystyrene has only 3. Glass has 65. Okay, so these graphs as well as tables and block diagrams are important for this chapter. Okay, now we'll continue with the topic Young's modulus. From this we can rearrange this to get extension. Extension delta L is equal to FL by YA. If you have many different wires, for example, steel wire and copper wire, you have two wires, steel wire and copper wire, both are of same length, but one is steel, other is copper. Same length, same radius. Same length, same radius. Both are applied with same force, same length, same radius. But the extension produced varies with Young's modulus. As steel has more Young's modulus. Young's modulus of steel is greater than Young's modulus of copper. So Young's modulus of steel is greater, that is why delta L of steel is much less than delta L of copper. So steel has small extension. That type of questions are very important. Also, if you use two steel wires applied with the same deforming forces, Young's modulus is same. So extension proportional to L by A. One which has more length and less area. Longer and thinner wire will have greater extension. Longer and thinner wire will have greater extension. That is also a previous question. So this formula to apply properly important. Delta L by L is equal to F by YA. Here delta L by L is called strain, linear strain. Linear strain is directly proportional to F by YA. Then linear stress is equal to Y into delta L by L. F by A equal to Y delta L by L. Delta L by L may be given in percentage. So Young's modulus into strain is called stress. So formula for Young's modulus is to be used very well. For determining the value of Young's modulus of a wire, you can suspend a non-weight below. Let weight be mg. Then you can find Young's modulus as mg L divided by A delta L, where delta L is the extension produced by that load and L is the unloaded length. A is the unloaded area, initial length, initial area, and Y is the Young's modulus. So this can be used for measuring Young's modulus of a wire. Young's modulus of a wire also depends on temperature. Not only Young's modulus, any sort of elasticity decreases with increase in temperature. On heating, elastic strength decreases. So Young's modulus also decreases on heating. Okay. Based on that, we can develop one more equation from this. Hooke's law, we have learned force proportional to extension. Force is equal to a constant into extension. So that constant here, rearranging this, get YA by L. So force constant can be measured like this. So force constant K can be written as YA by L. That is why in chapter work power energy, when we learned K is not to be inversely with the length. When a spring is cut into two equal pieces, the spring constant of each pieces will get doubled. because length halved K double. Ratio of length is 1:2. Ratio of spring constant is 2:1. So ratio of spring constant is the inverse ratio of length. K equal to Ya by L, K proportional 1 by L, F equal to Ya by L delta L, all this important. Now energy in a stretched wire. Energy in a stretched wire. Stretched wire has a potential energy because stretched wire is under the state of strain. And that formula is half into K into delta L square. This also is to be noted. Half Ya by L delta L square. So this type of questions have got a frequent history in asking questions in many of the competitive examinations. Potential energy can also be written as half into F into delta L. Can also be written as F square divided by 2K. All this formula relevant. Particularly this one. Energy equal to half into Ya by L into delta L square. Again, energy by volume may be called energy density. Energy density. So energy density of a stretched wire is the potential energy developed inside on stretching divided by its volume. Energy density is equal to energy by volume. Energy is half Ya by L into delta L square divided by volume. Volume is area into length, so area cancel. Energy density equal to half into Y into strain square. One more formula, energy density equal to half into stress into strain. One more formula, energy density is half into writing strain as stress by Young's modulus. You get half into stress square divided by Young's modulus. So stress square by 2y, strain square into y by 2, stress into strain by 2. This formula important. Also based on this you can write energy as energy density into volume. Therefore, energy is equal to, energy density is what? Half into stress into strain multiplied by volume of the wire. For example, this type of question may be asked. You have a stress strain graph. Stress on y-axis and strain on x-axis. You have a straight line graph. Stress strain graph is a straight line graph within elastic limit for all elastic bodies. Now, how to find the energy density from this graph? Energy density from this graph is area under that graph. Area under the graph is equal to area of the triangle half into stress multiplied by strain. And that is nothing but energy density. So by finding that area under the graph, you get energy density. Now, if volume of the wire is also given, you can find out energy, because energy density, because area, energy density is area into volume of the wire. The slope of this graph is stress by strain, that is Young's modulus. For all elastic materials, the stress strain graph generally, if you try to intentionally you try to find out the Young's modulus of a wire in that experiment, you may get a graph like this approximately. It is typical graph, stress strain curve of a metal. Okay, a wire is loaded and unloaded to plot this graph. Stress strain graph is linear. See, the Young's modulus is the slope of this graph. Slope is much larger, so it's a metal. All metals are having greater values of Young's modulus, particularly steel. Now from A to B it goes a curvature. Up to A, proportionality ends, so A is called proportionality limit. Beyond A, stress is no longer proportional to strain. But A to B, it is not proportional but remains elastic. Up to B, the body remains elastic, so B is called elastic limit. or called yield point. The corresponding stress is called yield strength. After that, again you load, stress increases, further strain also increases. But at the beginning, O to A, stress increases at a large rate. A to B, stress still increases with strain, but stress increase rate decreased. Rate of increase of stress decreased. B to C again C to D, stress increases, strain increases, but at smaller slope. Rate of increase of stress with strain is less. Derivative of stress with strain is less, but at D, the derivative becomes 0 because slope at D becomes 0. That's why that is the maximum stress that can be developed, called ultimate tensile strength, sigma U. Beyond that, the value of stress decreases. So that solid behaves as if it is a fluid, it starts to flow. The solid behaves as if it is a fluid so that it starts to flow. So at E, the point E, it breaks into two pieces called fracture point. The corresponding stress is called breaking stress. That is mostly, typically, nearly close to 30% of the total strain. Okay, if total strain is 1 centimeter, if total strain is 1 centimeter, 30% of 1 centimeter can be the point where it breaks into two pieces. And the substance remains in elastic region for less than 1% of the strain. See the huge difference between these percentages. Strain is expressed in percentage here. Okay, after that, we'll move on to the next elastic modulus, shear modulus. Shear modulus. Shear modulus, letter used is G, sometimes eta is also used. Shear modulus is equal to shear stress divided by shear strain. Shear strain is delta X by L. Let me show that picture in the textbook. Shear modulus. When a body is deformed such that the deforming force is parallel to any one of the surface which is farther from the fixed surface. The body is fixed at the base and a tangential force is applied parallel to the farther surface. Okay, then that linear dimension 50 centimeter mentioned here does not change. But there is a tangential restoring force developed inside which is against that tangential deforming force. That is the tangential restoring force. And here a small angle of shear called angle of shear phi. That angle of shear can be measured by using delta X by L. Phi equals delta X by L. Phi is called angle of shear, tan phi. Need not write tan because phi is very small, maybe 1 degree or less than that for elastic materials. That all depends on the size of the geometry of the body also. Phi equal to delta X by L. That is called angle of shear or shearing angle. Shear strain can be written as phi equal to delta X by L. Okay, so shear stress is this restoring force divided by area of the shaded part. That will be shear stress. So shear stress by shear strain will be shear modulus. Shear stress by shear strain is shear modulus. And shear modulus is very close to 1/3 of Young's modulus. That's very important, very, very important. Typically, the value of shear modulus of most of the metals are 1/3 of Young's modulus. So what is the formula for shear modulus? Shear modulus G is equal to FL by A delta X, sometimes can be written as F by A divided by delta X by L is tan phi. Tan phi, I am neglecting tan function as phi is too small. G as F by A phi. Then what is the formula for shear strain? Shear strain is equal to F by AG. What's the formula for shear stress? F by A equal to G phi. So how to find shear stress? You may be given shear modulus and shear strain, shear modulus into tan phi. Shear modulus into tan phi, but that phi may not be 30 degree, 45 degree, 60 degree, or what you know. Maybe in minutes or seconds. That's why that angle should be used in radian. G is in SI, given phi may be given as 1 degree, you convert that into radian and substitute to get the stress. So shear stress is equal to shear modulus into angle of shear. Angle of shear should not be in degree, it should be in radian. Convert degree into radian. That's all about shear modulus. The next one is bulk modulus. Young's modulus is mostly important here. Bulk modulus or hydraulic modulus. Letter use this B. Bulk modulus is equal to hydraulic stress by hydraulic strain. Hydraulic stress is numerically equal to the applied pressure, but equal to minus of hydraulic stress. Bulk modulus equal to minus of hydraulic stress divided by hydraulic strain. Hydraulic strain is the volumetric strain, delta V by V. So this is a popular formula used. The reciprocal of bulk modulus is called compressibility. Compressibility. Bulk modulus has its reciprocal called compressibility. So from this, what is the hydraulic strain? Delta V by V is equal to delta P by V. Numerically, you put minus sign here. This will correspond to a fractional decrease in volume. Fractional decrease in volume is corresponding to fractional increase in density. So for these two cases, the numericals may be asked. For example, as I told earlier, a ball is under depth of water up to few kilometers of sea water, and this depth is h. Then what is the fractional increase in the density of that sphere when it is taken to depth h? Then delta P is the extra pressure. That means, what is mean by extra pressure? When it was above, when it was at the surface, it would have been slightly bigger size. When it is taken to few kilometer depth, due to this hydrostatic pressure, it reduces its volume. So that's called volumetric stress. Then it increases its density. So there is a fractional increase in density when taken from surface to here. Okay, that event brings about an extra pressure. That extra pressure is this gauge pressure due to h depth of water. So delta P can be written as h rho g. You need not take atmospheric pressure there because it was atmospheric pressure at the surface. Now it is atmospheric pressure plus h rho g. So that extra pressure is that hydrostatic pressure. Delta P is h rho g divided by B equal to delta rho by rho. So we can find out what is the percentage increase in the density or fractional increase in the density of that solid sphere on immersing it to few kilometers of depth. Rho is the density of, rho is the density of water. Here delta rho by rho, rho is the density of the solid. Rho is the density of solid. Rho dash is the new density. Rho dash is greater than rho. Rho W is the density of water. We know density of water is 1000 kilogram per meter cube. Reciprocal of bulk modulus is called compressibility. This bulk modulus, this property can be relevant for solids, liquids and gases, all the three states of matter, but Young's modulus is only relevant for solids. What about shear modulus? Shear modulus is irrelevant for gases, but relevant for solids and also relevant for liquids when liquids are in motion. When two neighboring layers of liquid are in motion, a tangential restoring force appears between the two layers due to relative motion between two neighboring layers. That tangential restoring force developed between the neighboring layers in relative motion is called what? Viscous force. So viscous force per unit area is called shear stress, while two adjacent liquid layers are in relative motion. So when liquid is in under motion, we can say that shear modulus is relevant because shear stress develops. But if the liquid is at rest, there is no shear stress can develop in liquid. So shear stress is relevant for solids, but not for gases, but liquids sometimes when liquid is under flow. So that type of questions also may come in bulk modulus. Now we have learned Young's modulus, bulk modulus, and shear modulus. Another important topic is Poisson's ratio to be revised. Let us use this sigma. Poisson's ratio can be explained like this. We have a thin wire, elastic or metallic wire. On stretching, the length of that wire increases, at the same time its radius decreases. When length increases, there is a linear strain. But when radius decreases, there is a sidewise or lateral strain. Okay. So the connection between these two strains are found to be proportional on one another. When length increases, radius decreases. So if there is a linear strain, there is a lateral strain for all elastic wires. So lateral strain is found to be proportional to the linear strain. The proportionality constant appearing is called Poisson's ratio. So sigma equal to minus delta R by R divided by delta L by L. This formula is called formula for Poisson's ratio. Poisson's ratio can have values between 0 and 0.5. Poisson's ratio can have values between 0 and 0.5 practically. The practical varying values between 0 and 0.5. So Poisson's ratio may be 0.2, maybe 0.1, maybe 0.15, okay, maybe 0.4, like that. That varies practically. So the value of Poisson's ratio varies between 0 and 0.5. The last topic of the chapter is application of elastic materials. Few applications are to be discussed. One among them is bending of beam loaded at the middle. Bending of a beam loaded at the middle. Suppose you have a huge beam, supported by two knife edges, sharp knife edges. The distance of separation between these two knife edges for that beam is L. When that beam is loaded at the middle, the beam bends like this. When the beam is loaded at the middle, the load at the middle is mg. M is the mass. And here happens to be the depression at the middle, where L is the length. The beam may be seen like this. This may be that beam. Three-dimensionally, that beam may be shown to be like this. Beam having rectangular cross-section is in our syllabus. Different cross-sections may be there. We have in our syllabus beam having rectangular or square cross-section. L is the length of the beam. B is its breadth and D is its depth. An area of cross-section of the beam is breadth into depth. Okay, on loading at the middle, beam bends as if it is a shape of U approximately. Okay, not deformation is not considerable, very small deformation, because all this elasticity is much larger. The formula for that depression at the middle when loaded at the middle for a beam having rectangular or square cross section, formula mg. M is the mass suspended at the middle for loading it. Mg L cube divided by 4 YB D cube, where Y is its Young's modulus. So delta proportional mg, delta proportional L cube, delta proportional 1 by Y, delta proportional 1 by breadth, delta proportional 1 by depth cube. delta is to be minimum. Delta is to be minimum, for which length is to be minimum, load is to be minimum, Young's modulus is to be maximum, breadth maximum, depth maximum. As in length and depth, the power is 3. Maximum depression variation can be brought about by making changes in length and depth. But changing length is quite impractical because the effective space between these two knife edges will be reduced. The separation between two legs of a bridge reduced means that cost increased. Also, few more legs may be there in water. It makes cost not cost effective. That's why the practical way to minimize depression is to increase depth, for which depth is to be increased. So practical way to minimize depression at the middle when loaded at the middle is to increase depth. But on increasing depth, the problem comes. On increasing depth unevenly, like this is the length and this is the depth. I am not showing the breadth. The beam is likely to bend. Like this, as shown in picture. Such a bending due to excessive load at the middle due to excessive increased depth called buckling. So buckling is not good for engineering because it may be the buckling may increase the chance of a permanent deformation. So buckling is to be avoided. But depression at the middle is to be reduced. So depression is to be reduced. Buckling is to be avoided. The most suitable engineering shape is used, that is called I-girder or I-form girder, sometimes called I-section. Two uses are there for I-section. If beam whose cross section is designed as I-section, the material cost is less because this much of part, the shaded part of material can be avoided so that the cost can be reduced considerably. Buckling also reduced by using this I-section. So I-section or I-form girder, I-section or I-girder. Okay, rail track, the iron tracks of railway appears to have this cross section. Pillars appears to have this cross section. Beams of metro rail, you can see railway overbridge beams appears to have this cross section to sustain large load at the middle to avoid buckling as well as reduces depression at the middle. That is called I-girder or I-section. Another application is that a mountain on earth cannot be taller than 10 kilometers. The maximum height of the tallest mountain is that Everest is slightly more than 8,848 kilometers. Recently, a survey was done and noticed that the height of Mount Everest has slightly increased, but it cannot be taller than 10 kilometers because of this large shearing stress at the base of the mountain. A tapered cross section you imagine at the base of the mountain, the tapered cross section, shear stress developed. Large amount of shear stress on increasing the height, increasing the weight, increasing the shearing force. From the top part of the mountain to the cross section, there is a sliding occurring on the mountain. The mountain can slide slightly so that the height is reduced. So height of mountain cannot be greater than 10 kilometer. Maximum height can be 10 kilometer. That can be shown. While designing rope of a lift, you can find out the minimum area required for the rope of the elevator or lift to sustain a given load. For which you can use this formula: force is equal to stress into area. The maximum force, braking force, is equal to braking stress into area. So the maximum force is equal to braking stress into area. For not braking, force should be less than or equal to braking stress into area. So area should be greater than or equal to braking force by braking stress. Area should be greater than or equal to braking stress by braking force by braking stress. Then minimum area required is equal to braking force, safe load, divided by braking stress. That implies safe load may be given divided by value of braking stress. So this can be the minimum area of the elevator rope. Okay, all these type of questions are very important and also asked previously. Maximum load is called that safe load. Sigma B is called braking stress. Repeating, braking stress is equal to braking force by area. Braking force equal to braking stress into area. Braking force depends on two factors: material as well as area. More area, more the braking force. Less area, less is the braking force. On doubling the area, braking force of a wire is doubled. But braking force does not depend on length. If you make a metallic wire into two equal pieces, the maximum load that each of those wires can sustain is remaining same. The maximum load of a given wire sustained is W. Break that wire into two equal pieces. The maximum load that half the wire can sustain is also W, no change. That can be explained by using this formula. Okay. Also, if you have a beam is held tightly between two rigid walls. A beam is held tightly between two rigid walls. Beam is of length L, area A, Young's modulus Y, and coefficient of linear expansion alpha. You heat it from below. Heat it uniformly. What would happen? On heating, all metallic solids would expand. But there is no such provision to cope with this expansion. So what happens? The beam tries to bend. Suppose you resist the chance of bending. Do not allow to bend. Do not allow to expand or bend. Don't allow this beam to expand or bend. Then what happens? A stress will develop inside. Due to that stress, the change in length due to heating is balanced with change in length due to this load from both sides. So delta L is equal to L alpha delta T. L alpha delta T, where delta T is the change in temperature. Alpha is the linear expansion coefficient. Delta L equal to L alpha delta T. One more formula for delta L due to mechanical force. Delta L is equal to FL by AY. Equate these two. L alpha delta T equal to FL by AY. L gets cancelled. So F is equal to Y A alpha delta T. So this force is developed inside Y A alpha delta T, and that's subsequent stress F by A is equal to Y alpha delta T. This is called thermal stress. So maybe asked about thermal stress, that part is also important. This is a formula for thermal stress. Thermal strain also can be produced from this. Thermal strain is equal to delta L by L is equal to what? F by YA. F by YA. Thermal strain can be measured as alpha delta T. F by YA is the formula for strain. Here this strain evolved only because of this change in temperature. So thermal strain is equal to alpha delta T. So all these type of questions are asked frequently in examinations, recently for mains papers also. Okay. Anyway, we have completed the quick revision of chapter mechanical properties of solids, and I have also tried to explain maximum possible previous question seen in question papers. Okay, we will be soon meeting with the next chapter. Thank you.